this morning by Hiroyuki Inou from Kyoto University, and title of the talk is Infinite Adjacent Renormalization for Cubic Polynomials and Combinatorial Rigidity. Thank you.
Thank you very much for the introduction. And I'd like to thank the organizers for giving me an opportunity to speak here. And so, since I've been collaborating with Sabia for many years, we didn't have opportunity to visit each other until recently. And last year, so for the conference of Mitsu, Sabia visited us in Kyoto, and finally I have an opportunity to visit in India. So I'm very glad to come here and give a talk. Okay, let's start. So I'd like to talk about infinite renormalizations, and there are many overlaps with yesterday's Dabu's talk. And so I'm glad that he had already prepared many notions. But anyway, so I'd like to repeat some of them and complicate. I will succeed to skip one of the most complicated part. Anyway, so let me explain from the basics. So I'd like to talk about the cubic polynomials, but let us start the quadratic family. So it is easy to see that any quadratic polynomial is affinely conjugate to the polynomial of this form. So we only need to consider this family. And so let us define the field-Julia set. It's a set of the initial point whose forward orbit is bounded, and we denote it by k of qc or k of f for polynomial f. And so there is a nice dichotomy saying that for quadratic polynomials, either the field-Julia set or equivalent to the Julia set is connected, or it is a control set. And the Mandelbrot set is by definition is a set of parameter C such that the field-Julia set is connected. And this is a famous picture of the Mandelbrot set. And the black region is a Mandelbrot set, and the colored region is a complement. And it is easy to see that the Mandelbrot set is closed, so the boundary is also contained in the Mandelbrot set. And so, as in the Dabu's talk, so the renormalization is a very important object to study the complex dynamics in one variable and so on, and study the self-similarity in the parameter space. So let me give the definition of the polynomial-like map. So a map f from u prime to u is called a polynomial-like map of degree d. So we abbreviate polynomial-like by PL, and be careful that in the Mitsu's talk yesterday, PL is for piecewise linear, but I'm not talking about piecewise linear maps, just polynomial-like mappings. So a map is called the polynomial-like mapping if so the domain and the range are topological disks in the complex plane, and the domain is a relatively compact subset of the range. And the map F is a holomorphic proper mapping of degree D. So the definition is very simple, and my former supervisor was working on algebraic topology and not familiar with complex dynamics, and when I explained this notion to him, why this is called polynomial-like, how? So from the definition, it's difficult to see it's really polynomial-like. But anyway, so the simplest example is, of course, polynomial. So any polynomial of degree d greater than 2 is a polynomial-like map of the same degree if it is restricted to an appropriate large disk. So precisely speaking, take a very large disk, then take the inverse image. Then so the polynomial is a polynomial-like from this inverse image to the large disk. So this is a simple example. And in fact, this is called polynomial-like because there is a famous straightening theorem by Dwyer and Hubbard. So saying that any polynomial-like map of degree at least 2 is hybrid equivalent to some polynomial of the same degree. So in this sense, so up to hybrid equivalence, polynomial-like map is really a polynomial. And moreover, so if the field-Julia set of this polynomial-like mapping, so this is defined by this. So this is a set of initial points whose forward orbit stays in U prime forever. And so if the field-Julia set is connected, then this polynomial hybrid equivalent to this given polynomial-like map is unique up to affine conjugacy. And so let me skip the definition of the hybrid equivalence. So roughly speaking, so hybrid equivalence is a quasi-conformal conjugacy between two maps near the field-Julia set. And we also require some regularity in the field-Julia set. So the derivative is equal to 0. Anyway, so we don't need to go into detail. But anyway, if they are hybrid equivalent, they are conjugate near the field-Julia set. And so normally in the one-dimensional complex dynamics, renormalization, the term renormalization is used in terms of polynomial-like mappings. So let me give a rough definition of the renormalization. So starting from polynomial f of degree at least 2, and we say this map is renormalizable at some critical point C, and this renormalization is of period P if there exists a polynomial-like restriction of piece iterate of low degree. So I don't want to go into detail, but anyway, so in this talk, we just consider, mostly we just need to consider polynomial-like restriction of degree 2 or 3. So the piece iterate, for example, especially when P is large, so piece iterate of F has degree d to the P, which is very large, but the restriction has only degree 2 or 3, at most 4. Probably the degree 4 case doesn't appear in my talk, but anyway, so for quadratic or cubic case, we only consider degree 2, 3, or 4 case anyway. And so we also require the renormalization must have a connected field-Julia set. And of course, so we say that it's renormalizable at C, so the C must be contained in the domain. So this is a rough definition of the renormalization. So in the higher degree case, so the combinatorics, there are many critical points, and the combinatorics can be complicated, but let me skip this. We only consider very simple cases. And this polynomial-like restriction is called a renormalization of F. And so if a map is renormalizable, then by the straightening theorem, there exists a unique polynomial P, which is hybrid equivalent to this renormalization. And this is unique up to affine conjugacy. So if a map is renormalizable, then so you can assign a new polynomial of low degree by the straightening theorem. And we call it, this polynomial P, the straightening of this renormalization. And so as in the Taboo's talk, so renormalization can have another renormalization, and so on. So in other words, so for the original dynamics, so the second renormalization has a higher period than the first renormalization, and so on. So we say a map F, a polynomial F, is infinitely renormalizable if there exists a renormalization of arbitrarily high period. or you have, infinitely many periods such that f has a renormalization of period p. And so the renormalization is related to the self-similarity of the Mandelbrot set, or maybe the boundary of the Mandelbrot set. And so Douady and Hubbard proved that if you have a critically periodic parameter, so let's C naught be the parameter in the Mandelbrot set such that the origin, the unique critical point, is periodic of period P. Then, so you can find the baby Mandelbrot set, a small copy of the Mandelbrot set, which we call M of C naught. So this is homeomorphic to the whole Mandelbrot set, and it is centered at C naught. So more precisely, there is a homeomorphism from this baby Mandelbrot set to the whole Mandelbrot set, which we denote chi of C naught, such that, of course, C naught is contained in this baby Mandelbrot set, and by this homeomorphism, this C naught is mapped to the origin. And for any, precisely speaking, except at most one parameter in this baby Mandelbrot set, QC has a period P renormalization, so the same as this period of the critical point for C is equal to C naught. And this renormalization is hybrid equivalent to some Q C prime by the straightening theorem. And this C prime is equal to the chi of C naught of C. So this correspondence from C to C prime is given by this homeomorphism. In other words, so the straightening of this renormalization is Q of C prime. And this gives the homeomorphism between the baby Mandelbrot set to the whole Mandelbrot set. And so there are some examples of the baby Mandelbrot set. So this picture already appeared in Davu's talk. So this is a period 3 baby Mandelbrot set called the rabbit case. So this part, so although the cusp here is open, but anyway, so this part, well, there are some more decorations, but anyway, so somewhere, some subset in this part is homomorphic to the Mandelbrot set. And this is a period 4 case. The movement is, anyway. Yes?
The homomorphism itself, is anything known further? I mean, how wild is the homomorphism? Because
So for the
homomorphism is not a very interesting statement.
So for this so-called the primitive case, the homomorphism is quite conformal, in fact. And in the interior, it's analytic. But for this case, so since we opened the cusp, so it cannot be quite conformal. So if you need to remove a neighborhood of the root to get some regularity. So this is period 3, period 4, and I don't remember those ones. Maybe 26 and 260 something. But anyway, so there are a lot of baby Mandelbrot sets, and it's dense in the boundary of the Mandelbrot set. Of course, you can construct a baby Mandelbrot set in the interior, but it doesn't make sense. So basically, we're only interested in the boundary. And this homomorphism is called the straightening map. And well, I don't know if I use this term, but anyway, so the inverse operation of straightening is called tuning. And so So anyway, let us explain another notion. And so external rays and rational lamination are used to express the combinatorics of the dynamics. And this also gives the combinatorics in the, or yeah, this combinatorial, this also allows us to argue combinatorial property or topological property in the parameter space. But anyway, so consider a monic polynomial of degree, no, so this must be 2, I think. And we assume, so in this talk, basically we only consider the connected Julia set case. And then, so there exists a Bezier coordinate. So Bezier coordinate always exists, but we can extend. So assuming the field Julia set is connected, we can extend to the whole complement of the field Julia set. And this gives a conformal isomorphism from the complement of the field Julia set to the complement of the closed unit disk. And such that, so this is just a simple normalization. And anyway, to guarantee the uniqueness. And anyway, so the important thing is this Bezier coordinate gives the conjugate from the original dynamics to the monomial, just the power to the d. And so another important thing is, so here in the complement of the closed unit disk, we have a nice polar coordinate. So in some sense, this Bezier coordinate gives a natural, dynamically natural polar coordinate outside the field Julia set. So the radial lines in this polar coordinate is called external rays. So for given theta in R over z, so it's not the argument, but so one term is 1. Anyway, so this is more, yeah, for a given angle. Anyway, so RF of theta is defined by this radial. So this set is just a radial straight line, straight half line of the angle theta, and pulled back by the Bezier coordinate. And we say this external ray, Rf of theta, lands at a point in the Julia set, which is equal to the boundary of the field Julia set, if this limit, so this part, so if R tends to 1, the ray, so in the original space, in the complement of the closed unit disk, this is just straight line, so it has a limit. But if you pull back by the Bezier coordinate, it might oscillate or do something bad. But we say that this external ray lands at some point if this limit exists and equal to this point x. And so this, yeah, so if we consider landing external rays, so we might sometimes have that 2 rays land at the same point. So we might have this case, so one ray and another ray land at the same point. Then so those 2 rays divide the plane into 2 components. So this, if you have such a relation, then so you can divide the plane into many parts. And since there, so because of this conjugacy, so there are some dynamical object. So by taking inverse image and forward image and so on, so you can get a nice partition. And in fact, it is known that if this angle is rational, the external rays always land at some point. So let lambda q of f, so this is we call rational lamination, and this is a equivalent relation on, no, this is wrong. So q over z, I'm sorry. So for all rational angles, external rates run. So we can argue if the landing point is the same or different. So this equivalent relation is defined by this landing relation. So two angles are equivalent if and only if those two rays, corresponding rays, land at the same point. So rational lamination, as I explained, so gives a divide the plane into many parts, and so we can, by using this information, we can argue the combinatorics of the dynamics. So using this, we can construct some Markov partition and so on. So it is a very important combinatorial object. So one important problem is so how much we can distinguish maps or initial points by using this combinatorial, the rational lamination. So we are interested in the connectedness locus, namely, so the set of polynomials of degree d with a connected Julia set or the field Julia set. And in the connectedness locus, so we consider if take a map in the connectedness locus, then so we can consider the rational lamination. And so the problem is if there is only one map with having this combinatorics, or there are a lot of maps. And the simple example is, for example, if the map has an attracting cycle, then so, for example, you can perturb it. And so, it's stable. So you can change the multiplier of the attracting cycle. Then so the shape of the Julia set and the dynamics on it is mostly the same. And in fact, this moves continuously. So it's not always the case, but we assume some, exclude those stuff. So we only consider polynomials with, well, probably no indifferent or attracting cycle. So anyway, yeah, it's not important. But basically, we consider the case all periodic points are repelling. And for such map, F in the connectedness locus, we say it is combinatorially rigid if the any G with no indifferent cycle or no attracting cycle either, and satisfy, they have the same rational lamination. Then, so the composition of the Bettier coordinate, so Bettier coordinate both gives an isomorphism to the closed unit disk. So you can pass to the complement of the closed unit disk to, so the correspondence of the polar coordinate. And this gives a conjugacy from F to G on the complement of the field Julia set. And so if we say F is combinatorially rigid, if in this case this composition of the Bettier coordinate extends to a quasi-conformal homeomorphism on the whole Riemann sphere. Yeah, so in particular, if you have an attracting cycle, then so you can quasi-conformally deform the attractive basin. So you can, so we don't require that this quasi-conformal homeomorphism gives a conjugacy on the whole Riemann sphere or the whole complex plane. But anyway, so we are just interested in the infinitely renormalizable case, basically. So all periodic points are repelling, and the Julia set, the field Julia set has no interior. So in this case, this extension is a topological conjugacy. Anyway, so more generally, in any case, so this extension is a topological conjugacy on the Julia set. And so the combinatorial rigidity conjecture is so for this, I think I have to assume that without non-repelling periodic point, all cycles are repelling. But anyway, so yeah, if it has an attracting cycle, this doesn't hold. So non-repelling, I guess. So if the polynomial, if a given polynomial has a connected Julia set and has no non-repelling cycle, then so it is conjecture. It was conjectured that such a map is always combinatorially rigid. And in fact, so this conjecture is false. Well, it is believed that this conjecture is true. Well, I will explain later, but for the quadratic case, I guess. But it is not true for the cubic case. So anyway, so there's another famous conjecture which we call MLC. So the Mandelbrot, it is conjectured that the Mandelbrot set is locally connected. And so it is not difficult to see that if the combinatorial rigidity conjecture is true for quadratic polynomials, then the MLC holds. I don't know about the precise history, but it looks like folklore, and anyway, it is written on the Dirk Schleicher's preprint. Anyway, so the combinatorial rigidity conjecture is very closely related to the local connectivity of the Mandelbrot set. And in fact, your course proved that this rigidity for quadratic polynomials, which is at most finitely renormalizable. So the only remained case is infinitely renormalizable case, and there are a lot of studies, but so let me skip. Yeah, some are explained already, I guess, in the Dimas talk or Davu's talk. And anyway, so for the infinitely renormalizable case, the combinatorial rigidity is equivalent that the corresponding infinite nest of the baby Mandelbrot set. So starting from the whole Mandelbrot set, since the map is once renormalizable, this corresponds to some baby Mandelbrot set. And for the second renormalization, we have another smaller baby Mandelbrot set, and so on and so on. So we have if you have a infinitely renormalizable quadratic polynomial, you have an infinite nest of baby Mandelbrot set. Baby Mandelbrot set which contains the given polynomial, and the combinatorial rigidity is equivalent that this shrinks to a point. In other words, so the intersection of those baby Mandelbrot set gives a combinatorial equivalent class. So the combinatorial rigidity is if this set only consists of one point, or it contains a lot more points. And so, well, in fact, the baby Mandelbrot sets, so we can also consider external rays in the parameter space for the Mandelbrot set, and we can do same combinatorics. And so there, the parameter picture and the dynamical picture are very much related. And similarly, in the phase space, so we can also consider the combinatorial classes, or maybe it's simpler. I mean, so from the rational lamination, so you have a lot of pairs of rays which divide the plane, and if you consider all those dividing rays, then so the problem is so each part of so you have a lot of, so I don't know, there might be something more. Anyway, so you consider all the external rays, so the plane is divided into many places, infinitely normally many parts, and so the combinatorial class is each component divided by those rates. And so in the phase space, namely for the Julia set, so there are non-trivial combinatorial classes. And so, for example, there's a theorem by Sorensen. There exists an infinitely renormalizable quadratic polynomial whose Julia set contains a subcontinuum without periodic or pre-periodic points. And so this, well, maybe I need to explain more. But anyway, so this subcontinuum, so you cannot divide by rational parameter arrays. I mean, using the rational lamination, you cannot divide this continuum, k infinity. And so I don't want to explain in detail. Well, I'm going to use the construction later. But anyway, so let me skip, at least postpone to the last of my talk. And so anyway, so this example is obtained by infinite satellite renormalizations. And satellite renormalization, I will explain later. But anyway, so it was already explained by Davoud. And and in fact, this theorem is also explained by Davoud already, because in some case, for the infinitely renormalizable case, you can have hairy contour set, right? And each hair in this hairy contour set, in Davoud's talk, satisfy this theorem. I mean, so each hair can be this k infinity. So in the Julia set, so combinatorial class can be non-trivial, but we believe that the combinatorial classes are trivial, at least for quadratic case. Yes?
So if you take any Julia set which is not locally connected, and you take some non-trivial limit set of array, what is the difference with any equation of some non-trivial equation of array? What is more in this continuum?
So, well, I have to think. Well, I cannot answer exactly, but anyway, so of course it's
the intersection of all the little Julia sets of renormalization.
yes. So for the original Sorensen theorem, this is given by the intersection of the field Julia set of the renormalizations. Yeah, so anyway, so this is closely related to the local connectivity of the Julia set. And if it's locally connected, so this thing cannot happen. So, yeah. And anyway, so let me continue. So for the cubic case, the combinatorial rigidity conjecture is false. And Henriksen proved that by giving an example of cubic polynomials for which the combinatorial rigidity doesn't hold. And in fact, he used the example by Sorensen. So, precisely speaking, so there is a cubic polynomial which has a quadratic-like restriction, hybrid equivalence to the Sorensen's example. Then so you have some continuum in the phase space. And so you have a quadratic-like restriction, which is hybrid equivalence to this map, this one. So this is Q of C infinity. So you have some very wild Julia set anyway here. And anyways, there is some continuum corresponding to k infinity. And since this map is cubic, there's another critical point. So this is called omega. And so we consider the case that this critical point is eventually mapped to this continuum. And then well, this is explained precisely in this, but let me just give a rough explanation. So we consider this captured case. So there's one critical point in the quadratic-like restriction, and the other critical point is outside. And under some iteration, this is mapped to this continuum, k infinity, or some compact set continuum corresponding to the k infinity in the previous slide. And when you perturb in a nice one-dimensional analytic set, so this picture, this part remains. So you have some nice one-parameter family on which you always have this picture. So quadratic-like restriction, which is hybrid equivalent to this one. And this part moves continuously, nicely, or this allows a holomorphic motion indeed. So then, so the difference, if you perturb, the landing point moves. So you can find another parameter. So for the original parameter, this lands at some point in this compact set continuum. And you can find near close parameter which land at a different point in this continuum. Then so those two maps are combinatorially equivalent, but the dynamics is different. So they are not topologically conjugate on the Julia set. So this is a counterexample for the combinatorial rigidity conjecture. So this is how Henriksen proved the combinatorial rigidity conjecture is false. And in fact, I also proved that we can even find the copy of the field Julia set. And I wrote for explaining this, but anyway, so yeah, in this way, so for the cubic case, we have some combinatorial class which is not shrink to a point. And so this is already known, but so in this talk, I want to give another example. So for the Henriksen example, so although the combinatorial rigidity is false, but so there are two critical points and which are separated by rational lamination. We can distinguish two critical points. So I want to give a new counterexample today for which those two critical points you cannot distinguish combinatorially. In other words, so I can construct a cubic polynomial such that which is not unicritical. So you have two distinguished critical points, and F has infinitely many cubic renormalizations. Namely, so the domain of definition of each renormalization contains both of the critical points. So in particular, such a map is combinatorially equivalent to an infinitely renormalizable unicritical polynomial. So with the semi-combinatorics, you can construct an infinitely renormalizable polynomial which has only one double critical point. So this is another counterexample for the combinatorial rigidity conjecture for cubic family. And moreover, so with help of near parabolic renormalization theory, so we can make F satisfy that, so one of the critical points is recurrent, but the other critical point is not recurrent. More precisely, so this has a Hairy Cantor set, and one critical point is in the Hairy Cantor set at the end point of some hair, but the other is outside the Hairy Cantor set, but this is mapped to the Hairy Cantor set by one iteration. So then the orbit cannot escape from the Hairy control set. And moreover, from the construction, we can see that there is a continuum containing both. I mean, F is a map we constructed, and G is a corresponding unicritical polynomial. And so this combinatorial class contains a continuum containing both F and G. And in fact, so G is unicritical, and F can be very close to the polynomial which has this form, or affinely conjugate to this form. So, yes, Lima?
Generally, the only way for a map to be combinatorially equivalent to unicritical map, but not coincide. Would you expect that this is the only pattern? It's a combinatorial class for a unicritical map.
So I don't know how the combinatorial class looks like, and so I can say that this contains a continuum. I mean, so I even maybe it's possible, but so far I don't know if this combinatorial class is even connected or not. So at least I can say it contains a continuum containing those two maps. And so if time allows, I'd like to explain that. So we have some idea to show that we, in fact, have an arc in this combinatorial class. But this arc, I mean, what we can prove is, if we can, if succeeded to prove, this arc can be very small. So I don't know what happens for the rest. And so anyway, so this is not so difficult because from the construction, so we can easily find a path. I mean, so we construct finitely renormalizable polynomials and taking a limit, and in each step we can find a path connecting two maps, which is contained in the renormalization locus. Then by taking the limit, we can obtain a continuum. And anyway, so let me explain what is written here. Some I have already explained, but anyway, so such F is infinitely renormalizable in the polynomial-like sense, but also in the sense of near parabolic renormalization. And this allows us to argue how the post-critical set looks like. So in particular, so the Julia set contains a hairy contour set, and so this is why, so we have we know the post-critical set. So I already said that. So the one critical point is, so our class, which is invariant under near parabolic renormalization, basically contains only one critical value. And since for this map, so the critical values of those two critical points are different, so it can contain only one critical point. And so we restrict to have the map to have a renormalization, and the domain of definition of the near parabolic renormalization can contain only one critical point, and the other critical point is excluded. So the critical point contained in the domain is in the hairy contour set, and the other is outside the domain of definition of the near parabolic renormalization. So the other cannot, so the other is excluded. And from the construction, you can easily see that, but the critical value is contained in the hairy contour set, or in fact, the invariant contour set in the subset, where the hair, the endpoint of the other endpoint of the hairs. So because of that, we can see the dynamics of the shapes of the post-critical set. And so well, so I'm thinking about how to prove the existence of an arc. That this is by the, so since this is, so I mean, we can consider the stable manifold of the near parabolic renormalization. Then so there must be some continuous family of the hairy contour set. And by shooting by the other critical point, so we must be able to have some hair. We must be able to show that there exists a hair in the parameter space or in the combinatorial classes.
Where is this map G in the multiverse? What combination?
So this is just going to satellite of satellite of satellite and so on. So it's basically the same as the Sorensen's example. And so let me show many pictures. And I don't know if I have time to explain the proof further. But anyway, so we want to go to satellite of satellite of satellite and so on. So for example, we start from the parabolic map. So a polynomial having a parabolic fixed point at the origin. And this is simple parabolic or just a double fixed point. In other words, so the coefficients of the d squared is non-zero. And we consider perturbations of this form. So just change the multiplier of the origin. Just give a small rotation. So e to the 2 pi I over q. And basically, we only consider the case q is very large. And then, so fq, as q tends to infinity, converges to f naught. And so when q, so we assume q is an integer, large integer basically. So then fq has a parabolic fixed point of rotation number 1 over q at the origin. So for f naught, we have just parabolic fixed point and some parabolic basing. And when you perturb, so the fixed point divided into 2, and 1 has a parabolic basing of, I mean, so q parabolic basins are attached to it, and it rotates this way. Anyway, so counterclockwise. And so as q tends to infinity, those two critical points get closer and closer and collapse in the limit. So the picture looks like this. Oh, it takes some time to. So this is a cubic case. So this is a cubic unicritical family. So the left one is a parameter space of so d q plus c, and zoom into some point. So this is a 1/3 satellite. So we have a copy of the whole degree 3 Mandelbrot set. And so if you pick parameter somewhere here, maybe in this case we must take the parabolic parameter, but in order to get a visible picture, in fact, I took somewhere in the here. Anyway, so the middle picture is unicritical Julia set. So this has a period 3, and at the center there is a double critical point. And so this one is starting from this polynomial f naught z times 1 plus d squared. So in this case, the origin is fixed point, and the preimage of the origin is a critical point. So -1 is critical point, which is mapped to the origin. So the origin is here and have a 1/3 rotation. And the preimage here, -1. This is mapped to the origin. So at the origin, we have 3 components. And at -1, so it's so slow. There is so here at the origin, here we have 3, and here we have 6 components attached to the critical point here. So, and when I increase the q, so for q is equal to 4, we have this. So the picture is more or less similar, but we have 4 components around the origin and 8 components around -1. And so in this case, there is another fixed point. Well, there are 3 fixed points, but I want to ignore one of them. So there's a fixed point here with 1/4 rotation, and another fixed point is somewhere here of rotation number 0. And as q increases, so the next picture is q is equal to 10. Then so in both pictures, in this case, so the fixed points are here and here, here and here. Anyway, so they get closer and closer. And this is for q is equal to 100. Maybe I have to enlarge. So then it's hard to see. So the fixed points, but anyway, somewhere here and here, I guess. And here, here. I don't know. Anyway, they get closer and closer. And finally, in the limit, they collapse and get just a parabolic fixed point. So we consider this sort of satellite maps and take a satellite of satellite of satellite and so on. And so for the arguments, I think it's better to treat parabolic cases. But so for the picture, I can only draw, unicritical case and some attracting case. So this is more or less the same picture, but it has an attracting, super attracting cycle, I think. Anyway, so this is 1/3 satellite. And so this consider then 1/4 satellite. So, well, I guess this is a 1/2, 1/3, 1/4 satellite is here, I think. It's hard to see. Anyway, so 1/4 satellite is here. And if you took the center of this parameter, you get this Julia set. So here is a fixed point of rotation number 1/3. And here is period 3 cycle of rotation number 1/4. So the critical point is mapped to where? Somewhere here, here, and go back. But anyway, so in the third iterate, this point is mapped to here, 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 and go back. And then so this is a 1/4 limb of 1/3 limb. And then so I'm going to take 1/5 limb around here. Then so we get this picture. So this has a 1/3, so fixed point of 1/3 rotation, period 3 cycle of 1/4 rotation, and next, where is it? Probably here, I guess. Here we have a period 12 periodic point of 1/5 rotation, and so on. And so this part, the central part, has a super attracting cycle of period 3 times 4 times 5. So it's 60. And so basically we repeat this process. And if the Q is so in this case, so the fixed points and the periodic points of period 3 and period 12 cycle, they are far to each other. But if Q is very large, as I showed in the previous slides, so they get closer and closer. So we can, if you take each time this denominator Q very large, then so they must be very close. But it's hard to draw picture, and let me show just those simple ones. So anyway, so I don't think I have time to explain the detailed construction. But anyway, so we use some QC surgery or some realization from combinatorics to construct this satellite of satellite of satellite of satellite and so on. But so we don't start from the unicritical map, but we start from this map with a critical preimage of the parabolic point. Then when you perturb, so you have a, so for the first case, we have a parabolic fixed point at the origin, and -1 critical point is mapped to the origin. And the second case, so this, when you perturb, this has a the origin is divided into 2 fixed points, and one is repelling, and so we have spiral, and the other has some, so 1/q rotation. And we took a parameter so that the critical point, which is a perturbation of -1, is mapped to this fixed point of 1/q rotation. And the next step, so we again perturb. Then so we have a, and so in this case we assume that this is parabolic. Then so when you perturb, this parabolic fixed point bifurcates. Then what you get is one fixed point and one period Q cycle. So for the next step, we make the next map so that the critical point is mapped to this period Q cycle by one iteration. And repeat this process. And so let me show some picture. So this is a, yeah, so this is what I can draw. So anyway, so the first Q1 is 3, so it's very big, and two fixed points are very far. But anyway, so this is a picture for the second step. So the fixed point, we have 2 fixed points here and here, and the critical point is mapped to this fixed point by one iteration. And so I increased the second. Well, this is more or less the same. So no, so I'm sorry. So I said something wrong. So there are fixed points here and here there is a period 3 cycle, right? So my parameter, I choose the parameter so that the critical point, so the period 3 fixed point and the critical point in the renormalization are mapped to somewhere in the same point. Yes? Okay. So, well, let me, by doing this, so we get such a counterexample because the critical point, so the fixed points of the renormalization in for each renormalization, the fixed point of the renormalization is very close to the fixed point of the original map, and the further critical point is mapped to this point by one iteration, and the other critical point is somewhere in the middle of those 2 points. So we have a big continuum in each. So the field G set has this big diameter for each iteration, and by taking the limit, we have a counterexample in that theorem. So okay, I stop here. Thank you very much.